glory to our Almighty God for giving us this wonderful opportunity to join together for this webinar. On behalf of CSI College of Engineering, I welcome our chief guest, Professor Michael Moses T., Assistant Professor, CSE Department, School of Engineering and Technology, Christ, deemed to be University, Bangalore, Associate NCC Officer. And I'm also proud to say he's one of the alumni of our CSICE family. It's an immense pleasure for all of us to have you here to share your knowledge and experience with us. We welcome you, sir. I also welcome all the participants, staffs, and students present here for this webinar. Welcome all. Now I request Professor Ruth, Assistant Professor, CSE Department, to lead us in prayer.
Heavenly Father, thy throne of grace, may thy rule come into our heart more and more, and thy will be done in our mortal body. Thank you for giving us a wonderful day, Lord. The first thing that we would like to think now is to thank you for watching over us and for caring even when we don't ask. Thank you for blessing all our families until now. Thank you for protecting us from all the snares of evil. We pray for each and everyone who is going to attend the seminar. Please bless the Lord. Please bless the speaker, O Lord. Please bless us and guide us all through the session. We thank you for everything you've done to us. Help us and guide us to walk through the life of truth. We will not complain about what you allow because you know what is best for us. Thank you for everything, O Lord. We ask all this in the precious name of our Lord and Savior, Jesus Christ. Amen.
Thank you, ma'am. A passage from Bible, Proverbs chapter 2, 1 to 7. My son, if thou wilt receive my words and hide my commandments with thee, so that thou incline thine ear unto wisdom and apply thine heart to understanding. If thou criest after knowledge and liftest up thy voice for understanding, if thou seekest her as silver and searchest for her as for hid treasure, then shalt thou understand the fear of the Lord and find the knowledge of God. For the Lord giveth wisdom, out of his mouth cometh knowledge and understanding. He laid up sound wisdom for the righteous. He is a buckler to them that walk uprightly. Now, I hand over this session to our chief guest, Professor Michael Moses.
Okay, good afternoon to one and all. Thank you for that welcome. And it gives me immense pleasure to be a part of this webinar and back to CSICE as, as a speaker, as a guest speaker. And it is, I am overwhelmed, in fact. And thank you for this enormous effort by the department and all those people who have been part of this particular webinar. So I will share my screen right now. I hope you can see my screen.
Yes, sir.
And am I audible? Is it, am I loud enough?
Yes, sir. Yes.
Yeah, thank you. All right. So the topic or the seminar for today would be computer vision. And I would be trying to giving you or throwing some light on how we can carry forward or use computer vision to through research and help it, help build models and projects that can help mankind and as well as that can help a lot of social needs. So moving on. First thing, we need to know what is computer vision. So before we get into computer vision, we need to know the fundamentals of computer vision. So computer vision at present is one of the most sought after research arena. And the fundamental for computer vision is something we call as image processing. Image processing has been there for over a century, right from the inception of the first image that was taken. And from there is a success story of image processing by various means, various methods that probably many researchers have used in the time. And right now, any device that we use or any sensors that we use, image is something that is a part and parcel of uh, of it. Yeah. So image processing is something, or it's a system that can actually process images basically, and image is also a signal, and but it contains values that is arranged in the form of pixels. So image processing is a part of computer science that deals with how to study and how to enhance and how to make various changes to a particular image. If you can look at the image right in front of you, it is a robotic eye which we are trying to make a system to function similar to the human eye. So a human eye is a tissue, or it's an organ in the body which captures objects or captures scene and transmits it as a signal to the brain, and the brain processes and helps you to recognize that particular object. So when we look at an object, say you're looking at a ball, so it's very easy for you to know it is a ball. And if it's a cricket ball, it's very easy to identify it, or if it's going to be a tennis ball, because of the past learnings that we had as we were kids, as we were born as kids. We start to learn or start to understand uh, the different shapes, different objects. How do we understand these different objects? We try to understand it through learning, so through past experience, right? So that is something very important, and that is something that we need to transfer those kind of learning styles to the computer, right? So that is where image processing came into existence. However, computer vision helps, or is it's a branch of the whole of image processing, where you associate machine learning and artificial intelligence to image processing. So when you associate image processing with machine learning and artificial intelligence, then we call the entire process as computer vision. So with that brief background of what computer vision is, so basically, when we have to have a system that is artificially intelligent, and if it can be paired with image processing, the fundamental steps of image processing, how to read an image, how to extract data in an image, how to understand different parts of an image, how can you segment an image, how can you make a meaningful representation of an image. So these are few things that an image processing basically does, right? So when we can pair artificial intelligence through machine learning or deep learning, or any kind of machine learning techniques that we have in the recent trends, then we actually ensure, or we try to make the system more competent and more self-sufficient, that it can work by itself to detect, to predict, and make analysis of any data such as images that is given to it. So the basic goal of CV stands for computer vision, is to emulate human vision, visual system, like what I told you, to understand, to relate, to detect objects like what a human eye can do. Uh, that is what we are trying to help the system, or make the system understand, right? So before we get into that, let us understand the fundamentals, and then we will try to get into the fields of research. Today's topic, or today's work, or today's seminar would be based on image processing, to give you highlights on how research aspects are carried out in image processing. And maybe tomorrow's session will be on research on computer vision, where we will try to see what are the recent trends and research aspects of computer vision. So try to understand that computer vision and image processing are two different entities, but the base for computer vision is image processing. So you would have studied something, or you would have seen a lot of movies with a lot of computer graphics, right? So the base or the fundamental understanding of computer graphics is that we convert models meaning any kind of a model. It could be a paper drawn model, or it could be a three-dimensional model made out of paper, or it could be cardboard, or any kind of a model. And if you're going to convert into images, that means you're going to raster them and you're going to digitize those data, then it is called as computer graphics. So you try to actually create models first fundamentally, and then you make those models move, or those models animate, then they are called as computer graphics. So what is image processing? So we have an image. So image could be, in the olden days, we have images taken using films, right? We have olden cameras like Nikon, Canon, all of them picturizing or capturing images on films. Then we have to take it to a photo studio, and the photo studio person develops that image and he prints it on a photo paper for you. And that is how the images used to be way back, maybe 2 decades, 2 decades back. But now most of the images are digitized. And what do you mean by digitizing is when you're able to transfer the images from model or a paper or anything, and if you're going to convert them into digital field, that is, if you're going to convert them into ones and zeros, that is what computer understands. So if you're going to give them a tag called as ones and zeros, and then that is called as an image or a digital image. And when we do some processing on that, that is, when you want to say, that could be noise, or you want to add filters to them, or you want to enhance the image by adding brightness, illumination, hue, saturation, all of these things, then it becomes image processing. So that is where image processing comes into existence, especially majority of the work carried out, or majority of the research that is being carried out right now, undergoes something called as pre-processing. Pre-processing is something that is always carried out for an image before it is being utilized for various research purposes or research arenas. So image processing is something that you deal with image itself, and the outcome of that itself, of that process, is an image. But then when we move on to computer vision, we have images, but then we are going to convert, or we are going to make models, a face detection model, or a face recognition model, or an object recognition model. These are models that can detect specific tasks, or this can detect, or they are actually created for performing certain tasks. That is very vital, especially in this particular age, especially when you want face detection with surveillance cameras. You want to have object detection on cameras that are placed in front of your homes, that detects the movement, that you want to detect the growth of a plant. You want to detect the the trees, or how many what deforestation, you want to identify them. So these are models basically. So you create data is basically images. From data, you're able to transfer those information into a model that can basically learn, and that learning process can become an output or an outcome for understanding and to detect and predict various scenarios depending upon the image problem domain. So these are three different domains under computer vision or image processing basically, and computer vision's allied fields are image processing, computer graphics, and these computer vision. So I'm showing you an image here, and this image very well, we can see that it is basically a house, and there are a lot of plants in this place. You have windows, you have a door, there is a terrace, there is a place where the car can be parked, or a place where you can walk. So all of these are observations the moment you see a picture. That is what a human can do, right? So recently we can also tell that it has rained recently, and there are a lot of pots that has green plants. There are a lot of flowers on these particular plants, especially in the color of almost saffron color. So when a human being or a human eye looks at an image, it can make so many inferences. It can make so many observations, right? So that is something that a system cannot understand, or system cannot do it by itself, right? Even a human being, as the time when he is born or he or she is born, it takes a certain period of time for him to start making assumptions, start making observations, start making realizations of what an image could possibly be, or what an image contains, right? So it takes a period of time for you to realize things by yourself. So that is something called as a learning, or there is something called as a teaching, either by your parents, by your elders, by somebody who you are constantly in touch with, so that they teach you, they try to tell you that this is an object and this is the name of that particular object. So an object need not be the same everywhere in the world. It could have variations in shape, size, color, and so on. So but still the human eye, after certain observations, it is still able to make those differentiations and trying to understand those particular objects very efficiently and very correctly, right? So that makes the human eye, the human brain, very, very, very very sophisticated. That is the way in which a human brain works. uh, how do we make a computer, right? An ordinary computer which can process bits, the numbers, that is zeros and ones. How can we make the system also as efficient as a human being? That is the main goal of computer vision. So these are few questions that you can ask yourself. So what kind of a scene, this is a place where people live, and what are the plants, or where are the plants? So easily we can tell. So wherever there is green there you can tell that there are plants there, right? Of course there might be other green particles or green objects present in this particular image, but of course it is not there in this image right now. But we still can proceed and find out where exactly the plants are present and where the plants are not present, right? So that makes the distinction between a human eye and a computer. Yeah. So also we are able to detect a maximum size of a tall, how tall is the building. Is it a skyscraper, or is it a single story building, and so on and so forth. So you have distinctions, you have classifications being done, right? So this is something for you to understand how well computer vision recently have emerged as one of the most sorted research topic by a lot of researchers around the world. So this is another example how your visual cortex works. And we also have this blur and zoom in and zoom out, which are eyes which is capable of doing, but without automatically, without any interventions. You want to see a person who's standing far away, you can just concentrate on him. You want to see a look at a person who's close by, you will be able to concentrate on him. So this is how your visual cortex works, and that is how the mapping of information, or the mapping of the signal being sent from your eye, is captured by your brain. And it makes so much of analysis to understand what exactly an object looks like. Sometimes the brain gets confused, yes, because there might be a very close relationship between two different objects. But uh, once it is diluted, once this confusion is diluted, next time the brain does not make that particular get into that confusion mode, right? So that is something that our brain automatically maps and learns, right? So that is what we need to tend to make the system learn. So when we look at an object here, especially on a chessboard, I hope everybody would have seen a chessboard, and we also have a lot of objects on them. We basically could differentiate between a queen and a bishop, a king, a rook, and so on and so forth. Whatever sizes it might be, chessboards and chess coins comes in different sizes. Yeah, so though we play with different sizes of coins, we should be able to, a normal human brain would be able to differentiate between them without any problem by just looking at them, looking at those pieces just once. So why does computer vision matter and what has made it such a sought after research arena is because of we know that there is the surveillance camera which is present almost everywhere, and surveillance camera makes or continuously records data, and especially for safety and security, that is one thing that we rely on, and that is where we need to have. So when a security camera, it automatically detects a person or a person or an object that comes in your vicinity or in your surrounding, then it actually makes the human being alert, or a person staying inside the house, and the surveillance camera is capturing a person who has never come to your house before. So that actually makes a lot of sense, rather than a person who's staying alone at home, and if there is going to be an attack, if there is going to be a burglary, all of these could possibly be detected earlier. There could be an alert that is being sent to the person who's staying at home, so he would be ready, or he or she would be ready for it, right? So that is something where computer vision comes into existence. And health, where we want to analyze the growth of a tumor or growth of a baby, and various other things, especially with medical imaging and medical imaging systems. That is a lot of growth and lot of availability where image processing is presently being used. Then we have comfort, where automatic using point clouds, we would be able to create our own cartoons, or we can also create animated figures. And these image processing, automatic learning, and games that can automatically learn your movements, help you to understand, help you to play games better, and all of that. And if you want to search for an image on the internet, it's going to be very difficult. So if you have to have a face recognition software that can actually detect the faces online, especially with a lot of police agencies and so on. So these are few things where computer vision really matters, and it has placed itself as the eminent leader for research, especially in the field of image processing. So, and computer vision, the market has always been a boom. And in 2019, we can see the green graph, where we have about, especially in the consumer items, where it's about 15,000 or maybe more than $15,000 or US dollars. Yeah, I'm sorry, 15,000 million US dollars. And everywhere in majority of the domains which are listed out here, security and surveillance, medical, robotics and machine vision, consumer products like car sales, or a product, any product could be sold over the internet and so on. So you require computer vision, which can predict that a person is looking for a product, and he can enhance the look and feel of a product, and so on and so forth. So that is how the market has been in the last year, especially. And we can see that there is a lot of boom, especially in the automotive and robotics field, in par with the customer or consumer allied applications. Yeah, so a small history where we started with our computer vision. In 1966, Minsky is a person who started an undergrad summer project in one of those profound universities in 1966. So that project was to interpretation, and in 1960s we had interpretation of synthetic worlds. That is what I was talking to you about. When we have synthetic world, that is an object that is being created using synthetic data, that data has to be moved on to the computers and so on. So that is where the computer vision came into existence. And some progress on interpreting or selected images, where edge detection, you want to find out the different objects in an image, like you can do image segmentation and various other things, right? So that was in 1970s and 1980s. We have the artificial neural networks. They came and went, and they had this geometrical based systems basically, which could actually make more analysis on images. Those days, especially before 2000s and all, we probably did not have a computer vision field which can work on detecting images, detecting objects in an image primarily, but they worked on various other parameters like enhancing images, especially images that were received from various satellites, images that were received from various locations in and around the world, because those days we did not have bandwidth, or we did not have those data rates that we have presently to transmit data from one location to the other. If I have to quote you an example, there was a Bartlane cable that was laid between the London and the New York, and the first transmission of data or transmission of image that happened in 1921 was one example, where you transmitted data from London to New York for a newspaper. So that is where we started initially. So, and we are at this moment now, so we are somewhere close to detecting or recognizing face and statistic analysis on the Vogue and so on and so forth. So once 2000s and once we have crossed the 2000s, we had a lot of databases or a lot of images, especially in the US and Russia and China. They started working on how we can detect faces, especially in the field of crime investigation and so on, right? So they used to feed data into the system and try and search for those similar characteristics, or we call it as feature in image processing. So this is how the generation of image processing started, especially from the year 1966. So very brief differentiation between image processing and computer vision is what I put here. So it is like we have image processing, we have a raw input image, we are trying to enhance them, uh, or we are preparing that particular image for some other task, right? So whenever we take an image, or when we receive an image, those images would be of different dimensions, different resolutions, different sizes of pixels, and so on and so forth. So for your analysis or for the work that you are carrying out, you have to make some kind of an enhancement, some kind of a normalization process. So that is what we do under image processing. What do we do under computer vision? From the image that we have, we try to extract the information on whatever input images that we have, or on videos, or videos and images, and we try to understand. We try to understand, or we make the computer understand that these are objects, these are different kinds of objects. This is object X, this is object Y, and so on and so forth. The second point is image processing uses methods like anisotropic diffusion, hidden Markov models, independent component analysis, principal component analysis, filtering, noise reduction, so on and so forth. So these are options, or these are methods that is being used in image processing. So when we go on to the next point, that is on in computer vision. So image processing is one of the methods that is used for computer vision, along with other machine learning techniques, convolution neural networks, deep neural networks. So image processing is the underlying or the fundamental step that we basically carry out in order for us to have good good images that a system can learn from. And image processing is a subset of computer vision. Computer vision is a superset of image processing. Image enhancement, resize, frequency analysis, all of these are being carried out in image processing. And on computer vision, we can learn deep features. How do we interpret those features? How do we differentiate between good and bad, or how do we recognize various objects, and so on, are carried out over here. So few examples of image processing is resizing, rescaling the image, illumination changes, removal of noise, changing tones, color image processing, black and white image processing, grayscale image processing. But what we have in computer vision is we have object detection, face detection, handwriting detection, um, uh, uh, plant growth detection, leaf disease detection, tumor growth, tumor detection. There are a lot of applications, especially in the field of computer vision. So what are the fields in this part is the same thing what we've seen already, that is the image processing fields, computer graphics, image processing, and computer vision. So what is the input and output for image is for an image processing, we have image, and computer vision, it would be the description. And for computer graphics, we have the artificial intelligence associated with it. So sometimes, image processing is defined as a discipline in which both the input and output of process are the images, like what I told you already. So, but according to the classification, there are a few trivial tasks of computing. Like we calculate the average intensity of an image, we calculate the histogram of an image to identify where the maximum number of data is present. I will show you an example of how the data is distributed among the different pixels, and how do we use those images to understand what is there in the object, and so on and so forth. So that is basically what we do in image processing. So there are a few types of computerized processing, that is low level processing. So input is and output are images, and primitive operations such as to reduce noise, contrast enhancement, image sharpening, noise reduction, noise removal, filtering techniques, all of these comes under this low level process. Then we have mid level process where our image, basically we are dealing with images, and attributes are extracted from these images, especially edges, contours, identity of individual objects, or where exactly a particular object is present, in which location an object is present. So that is where the segmentation and description, all of these are taken care of, and various classification models can be incorporated over here to uh, identify different fields or different objects present inside the particular image. So this is mid-level process. And the high-level process is something that we're talking about, image analysis and computer vision, where the complete image is taken into consideration, and you make an in-depth analysis of where the data is being present, what are its neighborhoods, what pixels are affecting because of noise, and how can we eliminate noise by not removing the data from the image. These are few things. These are many of the things that image analysis and computer vision can combinedly give us. So low level, mid level, and high level processes are what we've seen right now. So basically, an image can be defined as a two-dimensional function, which is f of x comma y. And x comma y is a spatial coordinate. It is something similar to your graph, where you have an x-axis and you have an y-axis. And a spatial coordinate is the value of x and y, where the particular point or where the particular location is. If x is 10 and y is 15, that means we are looking at a position between x, where x is equal to 10 and y is equal to 15, and that particular point is marked, and we have data there. So f is the amplitude of any pair of coordinate x comma y, which is called as the intensity of the gray level of the image of that particular point. So when we talk about images are basically, presently we work on color images, and color images are all, color images have pixels. So even if you look at your screen, you have pixels. So these pixels have intensity values of red, green, and blue. So for any color format, for in any color image, we have red, green, and blue values. So these intensity values are ranging between 0 and 255. That is the maximum number of values that can be assigned for red, green, and blue, because it follows something called as a 8-bit color information. And so since it is 8-bit, we will have only a 0 to 255. So a particular pixel can have any random value between 0 and 255 for the values of red, green, and blue, right? So you can convert this entire color image into a grayscale image, which normally is being done in order for faster processing, because when we have a color image, we have 3 dimensions, and 3 dimensions are costlier, or you would require a computational a requirement which is greater than for a two-dimensional data. So when you look at a three-dimensional data, especially for RGB, that is, you'll have to process R separately, green separately, and B separately. You require sophisticated systems. So generally, all the images that is being used, especially when you want to have faster processing, they are downsized or normalized to something called as a grayscale, and the grayscale contains value as a single information or for every f of x comma y, right? So that is why I put here. So we have a f of x comma y, where f is the value of x comma y. X comma y is the point or the location of our particular pixel. And when we are, these are discrete quantities, right? They are not continuous quantities. They are not ranging between minus infinity to plus infinity. It is discrete between 0 and 255. That's why it is finite and it is discrete. And it need not be monotonous. It can be random. It can be discrete, and it will be, finite data. So this is something that you have to understand for an image. Whenever you look at any kind of an image, every image is being divided into uh, smaller values or smaller elements, which is called as pixels. And if I have to elaborate pixels, pixel stands for picture elements, right? So every picture element has a value. If it's going to be a two-dimensional data, then it's going to have a single value, which is x comma y, which represents a grayscale value ranging between 0 and 255 in that particular pixel. If it's going to be a color image, it's going to have three different values, RGB, and it will be placed for a particular pixel. So that is the difference between a two-dimensional and a three-dimensional image. And that is how an image basically is defined in the image processing. So what are the things that basically we can do under image processing is listed here. And that is first, the problem domain, or it could be an image. Then we acquire, first of all, the image is taken or images acquisized, and then we move on to image enhancement. Then it can be restored. Then we go in for color image processing, then wavelets and multi-resolution processing, image compression. So these are few things or few basic operations that is being carried out in image processing. And each each operations can be used or need not be used depending upon the problem domain. So if you have a very low intensity image or a very dark image, so you definitely have to enhance that image. So you have to use image enhancement. If there is not going to be any data that is lost, especially in your image, you don't have to go for an image restoration model, right? So these are few options that we basically have. However, it need not be used in full, and all of these operations need not be used on on a particular image, and only a specific list of operations depending upon the problem domain, depending upon the application, you should be, or you shall go ahead and use them. So this is what I was talking to you about. So this is, let's consider this to be an image, and every image, this is a spatial domain, and this is a grayscale image. And if you can look at it, each box which is there and it contains some values, those values are the pixel values, or the f of x comma y, which is being present inside this image. So these values, if you can look at it, is ranging between 0 and 255 and not more than that. And we have something that is being taken out as a 9 pixel values, which is 138, 134, 101, 119, 99, 83, 84, 80, and 79. So for a particular pixel, any pixel chosen at random in this particular pixel values that you have in the image, every pixel has neighbors. All right. So you have different ways of representing neighbors. You can represent it different ways different ways. That is, now what we have taken is, for the value or the pixel 99, you have values, or you have the pixels that is taken around them. That is 1, 2, 3, 4, 5, 6, 7, 8 pixels, which is being taken as their neighbors. All right. So this is very important, because sometimes when we want to eliminate noise, sometimes when we want to make image enhancement, sometimes when we want to use averaging, sometimes when we want to use min-max filters, right? At that point of time, we are not going to process the entire image at one stretch. We are going to take such kind of neighborhoods, and then we're going to process those images. So if you can look at them, they're not that very distantly placed, especially those pixels present here. They're ranging between 79 and 138. So they are distant. They're about distance between like 50 pixels. But when we look at a very closer range, you can also see that every pixel is distributed or has a good amount of difference between each values, right? So if there is going to be a noise, we can go exactly to a particular pixel and find out if that particular pixel is affected by noise or not, especially in a spatial domain. So whenever we are trying to process image, and when we're trying to make changes to those images in the spatial domain using numbers, and especially with those pixels, then we call them as spatial domain, and they are directly associated with various statistical approaches that we have, like averaging, median, mode, filters that we use, and so on and so forth. So they, whatever operations that we basically want to do, we will be doing it on pixels by gathering or using the neighborhood of those pixels. So you will be able to iterate these many number of pixels on every iteration. If you want to make, you want to change all the values in this particular pixel by taking an average of a average value, go ahead and we'll be able to make an average of all these pixels, and we will be able to uh, summarize it with a particular value if you find that this particular image is having any issues, especially with the noise and so on. If you want to enhance the image, of course you can enhance the image. So by improving or increasing the pixel values, if you have values, if you can look at the bottom of the screen, you can see that the values are tending towards 0. So if the values are tending towards 0, then we can say that those pixels are going to be very dark, right? And if the values are closer towards 255, then the image is going to be very white. So that is how the grayscale value ranges between. If the value is 0, it is dark, and if the value is 255, it is going to be white. So in between is where is the mix and match of both black and white intensity values give you different representation of grayscale values. All right, so this is spectral analysis. We have the first one that we looked at is the analysis that we're doing in spatial domain. The second one, what we're looking at right now, is the analysis that we will be doing in the spectral spectrum. It could be a Fourier spectrum or a cosine spectrum. It could be any spectrum, especially in the field. And you convert the image from the spatial domain into the frequency spectrum and make analysis of them. And you can look at the graphs that is being generated, especially with this, the first image, that is A and B. They are not affected by any noise or anything, so that you have a proper intensity graph there. But when you look at the other images where you have noise, and the third image, that is D image, is filled with salt and pepper noise, and G image is a blurred image. So you can look at the variations of the graph that is being given as C, F, and I, where you have the intensity of various levels, especially in the graph or in the image, is either tending towards 1 or it is tending towards 0. So that will be able to understand that this particular image is either blurred, or it is filled with noise, or if it is it is normal image. That is how we tend to make analysis of how well the images can be images can be processed, and what kind of images we are dealing with. So few research perspectives I would talk about. We will talk about a few or the recent trends where research is happening, especially in terms of image processing. The first one is the volumetric segmentation. On the right hand side, you can see the images of a brain, where we want to construct a 3D model of a particular part of the brain. So we basically use this volumetric segmentation in order to create uh, create a design, or create the exact hippocampi, or you can look at the position and the size and the shape of a particular organ or a particular part in a particular organ. So that is one thing that we basically do. So under medical diagnosis, or the first thing that we're looking at is medical diagnosis and treatment planning. We are basically looking at various medical images, and the first thing that we will be looking at is how we will be able to transform various parts of the images and try to have a volumetric segmentation using ROI. ROI stands for region of interest, and FA stands for fractional anisotropy. And that is how we are able to arrive at something called as a H, where we are able to exactly look for the segmentation. The first part of the segmentation is thalamic segmentation. And then we have the axial, coronal, and sagittal images, especially for a three-dimensional images. This is very important. Axial is the x-axis, the sagittal is the z-axis, and the coronal is the y-axis in the way the data is being stored. All right. So this is how a volumetric segmentation is carried out. And next we have something called as region of interest. Region of interest is very commonly used by a lot of researchers, not only in the field of medical diagnosis, but it is used in varieties of areas. And the previous example was to exactly detect a particular location of the brain to identify a particular organ inside the brain. But here we're looking at different positions where your images are segmented. And these segmentations are, if you can look at, they are divided into different locations. To speak very fundamentally, the top, bottom, the center, and so on and so forth. However, there are different ways of looking at these images, and each of these segmentation has its own uh, importance in why these segmentations are made, and different kinds of analysis are made on those particular segmentations. So this is region of interest segmentation. Next, we have something called as automatic detection of landmarks. So this is the first image is a skull where you have the face, the eyes, the nose, and so on and so forth. So if you're interested in detecting only the brain, especially the top part of the brain, then we can draw a line. That is, write an algorithm to draw a line by dissecting those images by top, bottom, and center lines. So after we have drawn the line, then we will be able to dissect them into images, dissect them into parts of the brain, and then make analysis on them. So this is automatic detection of landmarks. And landmarks, by landmarks I mean the importance fields or important locations of that particular image. These are X-ray images of a human brain, and this is what can be done for an automatic detection of landmarks. Next is tumor and cancer detection. We all know there are a lot of images that are present, and the MRIs and the CT scans that we take are able to detect the exact location of the tumors, and also the growth in which the tumors are present. If you can look at the left image at the bottom, how well we can zoom, and we will be able to exactly identify which is tumor cells and which are not tumor cells. And you can also see that there is some problem with the liver, and there is some kind of a cancer that is being detected in the one of the organ which is the liver, right? So this is another research arena where a lot of people are working on. And we have this automatic registration and fusion techniques. So this automatic registration or image registration is to transform different set of data, right? So by till what we have seen, we have been collecting only a single images and trying to make analysis on them. But what registration does is we are going to transform different sets of data on different types of data, merge them together, and in order for us to have them in one single coordinate system, and we will be able to have them registered as one single image. So you have a original image that is FDG PET image, which is a positron emission tomography. That is an image of that. That is an emission tomography image. And we have a CT scan image, which is at the bottom. You're combining both of these informations because CT scan gives you different information and your tomography images gives you different information. So by registering both together, you should be able to have, or a fused data should give you better understanding of different parts of the body. So that is some research that is being happening in under image processing, especially in the field of medical diagnosis. And then we have surface reconstruction. If you have images, and especially with points, and if you want to build on reconstructing a face, reconstructing a part of the body, and so on, we have to create models, and those models can be created using these many number of options that we have, especially with 3D point cloud, which is the recent trend that is generally being used by majority of the researchers, where the point clouds are a set of three-dimensional data, and by using them, you should be able to reconstruct a lot of data and so on, with help for medical diagnosis and treatment. This is superimposition, especially with the unraveling of various mummies and various other artifacts. If you want to create structures, or you want to try and see how well a face was during an ancient period, we have options. That is what we're trying to do here using superimposition, and we're trying to create a face using a skull, and with all of these basic informations, you can develop models that can create a face, and develop fully grown models to make them as a face. Next, we have agriculture sector, where we can detect seeds, we can analyze seeds, we can see if the seed is viable for planting or is not viable for planting, and will a particular seed give results, and will a particular seed not give results. So based on the shape, and based on the way in which the texture is, based on the way it is present, you should be able to make different analysis of analyzing the seeds, and to have them assist with their potential. This is another agricultural sector to detect different types of diseases. Diseases is something. Diseases in plants, especially in agricultural field, is one of the prominent areas right now, with sensors placed on the agricultural area. Development of diseases and development of the plants growth, all of them are being automatically detected. These are few places where we can have the plant disease detection looked at. What kind of a disease? So there are various diseases that a plant can be affected by. How well, or what is the rate of effect of that particular disease on a plant, and will the plant be able to recover, or will the plant be able to bear fruit? All of that could possibly be done using in the agricultural sector. Next, we have this automatic monitoring of plants, and categorization of plants by finding out the sepal length and the petal length, by detecting the color of the particular flower or the particular leaf. You should be able to say that this particular plant belongs to such design, or sorry, such genre, right? So that is something that also works with the agricultural sector. Next, this is very interesting, and a lot of people are working on this, which is monitoring applications, especially with radars and surveillance cameras. So these are few things that is always predominant and being widely used by a lot of people, especially to find out people walking, and to find out how many people are present, like people counting, if there is going to be a threat, if there's going to be any problem, to find out activity of a particular person, to constantly have a surveillance on a particular person. All of this is being done using this monitoring applications, and the surveillance is done. Surveillance is one of the major objectives, especially in image processing, by face detection and so on and so forth. Then we also can find out if there is going to be a leak, if there is going to be a fault, uh, especially in the industries, industry oriented, industry where image processing can be used. If there is going to be any problem, because if there is going to be a person continuously monitoring a particular plant which is present at the bottom, it is not going to give out good results. So it is always good that you rely on computer systems, right? So that is where monitoring applications for industries also plays a vital role. Next, we have this disaster management, especially for landslides and heavy, if there is going to be a rainfall and will there be a landslide. It could be done using hyperspectral imaging by having layers of images being taken into consideration, and you should be able to have different analysis being done for different spectral of data, and you will be able to detect this kind of informations, especially landslide, especially in places like ours, that is Uti or Kunur, or where there is where we have a lot of hilly areas. We should be able to detect and landslide prone areas and save people by using our image processing techniques. Then we have this underwater image processing, where it detects different types of fishes, different schools of fishes, and where exactly these fishes are, and where do they stay and how do they live, and all these analysis could be done using this underwater classification. And this is remote sensing, where we're talking about high spectral or hyperspectral dimensions. Not only the surface of the earth is taken as an image, but down beneath you would be able to have different layers of information being taken, and based on the spaceborne hyperspectral sensors, and that gives a lot of information, especially in the fields of change detection. That is, if you have a river and or a pond or a lake, how over a period of time has it changed? Has it changed its course? Has it changed its density? All of those could possibly be checked by these remote sensing remote sensing image processing. Flooded area detection, if there is going to be any person in the flooded area or in the vicinity of the flooded area. And then you can look at water quality, then the health of trees. You can detect deforestation, and you can also detect on how much of mines or how much of mining is happening in a particular area. All of these are possible because of this remote sensing and these image processing techniques that are being used, especially. And we can map borders, especially the rivers, the roads that leads to different paths, and something like a terrain view that you get in the Google map. We would be able to use them, right? So these are few applications that probably we should be using for image processing. And those various applications that we have seen are generally used for image processing. So with this, I will finish my webinar for today. We will continue about the various applications for computer vision tomorrow. If there are any doubts that you have, you can possibly ask me if time permits, and I should be able to answer it.
Students having any doubts? Thank you, sir.
Y-
Thank you for this wonderful session on image processing, computer vision in image processing and its research perspective.
Yeah, you're welcome, ma'am.
Thank you, sir. Waiting for your tomorrow's session, sir. Thank you, sir.
Thank you. Yeah.
Jerry, sir.
மேம் என் பண்ணிட்டுங்களா?
Yes,
Okay, sir.
Mr. Ma'am.
Sir?
Mr. Ma'am.
Ma'am?
Ma'am, kindly ask the students to participate tomorrow, ma'am. நாளைக்கு session கொஞ்சம் participate பண்ண சொல்லுங்க.
Ma'am,
இன்னைக்கு only 29 of them are participating.
groupல போட்டிருந்தோம் ma'am, but it's better that
No,
all the
sorry,
respective
sorry,
staff,
sorry.
the class advisor call them
Okay,
and tell them.
Okay, ma'am, we'll tell them. Okay. Okay, Manisha, then. Thank you.
Okay, ma'am. Thank you.
Jay, sir, thank you, sir.
Thank you, sir.